Hello students, today I shall discuss about tensile and compression test of engineering materials. Now, before the test we should understand what is stress and what is strain. In continuum mechanics, stress is a physical quantity that expresses the internal forces that neighboring particles of a continuous material exert on each other, while strain is the measure of the deformation of the material. In a simple case, we can write stress is equal to resistive force F divided by cross-sectional area of the specimen, whether strain is equal to for linear strain is equal to Li, that is final length minus original length divided by original length, that is change in length divided by original length. Now according to Hooke's law, we know that stress is directly proportional to strain, or we can write sigma stress is equal to E into epsilon, where E is equal to modulus of elasticity, and this is strain and this is stress. So stress is equal to modulus of elasticity into strain, or stress divided by strain is equal to modulus of elasticity. Now in tensile testing, we have this type of testing we can perform in universal testing machine. Now in universal testing machine, here we have to attach one specimen whose dimension is given here. The gauge length of the specimen is 2 inch and cross-sectional area is equal to pi by 4 into 0.505 square, or we can say the diameter of the specimen is 0.505 inch. Now we have to fix this specimen between these two jaws, and this one will remain fixed and this upper portion will move in upward direction. So in this portion there will be elongation, and that elongation will be measured by this extensometer, and load versus this elongation can be plotted graphically, and finally we can get this type of stress strain curve for a brittle material like mild steel. Now here initially up to elastic limit the curve is perfectly straight according to Hooke's law, but practically up to proportional limit the curve is perfectly straight, and up to elastic limit there will be no permanent deformation inside the material. That means if we remove the force, then the material will regain its original shape and size. Now here the length of the material will increase during loading, and as strain increases, stress also increases up to upper yield point. Then suddenly the stress will reduce for a moment, but strain will increase, and when the material get strain hardened, then again the stress as well as strain will be in increasing mode. Now graphically at ultimate point the stress value will be maximum, and at ultimate point the neck formation will start. Now neck formation, as the neck formation starts, then the cross sectional area at neck becomes smaller and smaller, and at fracture the value of the cross sectional area of the neck will be minimum. So the stress level at ultimate point will show maximum value for engineering stress strain curve, but practically at fracture point the stress level will be maximum. But it is quite difficult to measure cross sectional area, instantaneous cross sectional area during the experiment. That's why we consider initial cross sectional area or initial dimension during this experiment. That's why we get maximum stress value from this curve, that is ultimate strain, and at fracture the value is lesser compared to ultimate one. Now during compression test we have to put the specimen in bottom part, that means the upper part is this is reserved for tensile testing and bottom part for compression testing. Now here this is the setup for compression test, this is the specimen, and if this part moves in upward direction and this one remains fixed, then in this specimen there will be compressive force. Then dimension, that means cross sectional area of this one will increase, and finally we will get this type of curve. Here we will get always, as there is no neck formation, then we will get this type of curve, and at fracture point the value will be maximum. So there is no ultimate point, directly we get fracture point, and maximum value we will get is called breaking stress. Now stress strain curve for cast iron, steel and zinc. Steel and zinc both are ductile material and cast iron brittle material. Now in case of zinc and steel, elongation is very high compared to cast iron. Now here we will not get any yield value, and directly we will get the normal breaking stress. Now for steel we will get upper yield point as well as lower yield point, but for aluminium, zinc, this type of materials there is no specific yield point, directly we will get breaking point. This curve is for compression test and compressive stress versus compression strain. Thank you for patience.